Hello, we're Team I28 from UBC School of Engineering, and I'm Ishita.
I am Scott.
I'm Jason.
I'm Alqeshira.
And I'm Will.
And I'm Jules. And we're proud to present PUPPETRONICS.
In the dark, a story begins. This is The Raven Stealing the Light, a sacred story from First Nations heritage. But for millions of children, the light of modern STEM education remains out of reach.
Globally, only 40% of primary schools have internet connectivity. This connectivity gap means millions of students are excluded from the hands-on STEM learning, essential for the modern world. Our project will change that. Our expanded kit is designed for deployment to First Nation communities in Canada and classrooms across Indonesia and the Philippines. While other existing commercial robotics kits cost a fortune, we created something entirely unique. PUPPETRONICS is the first robotics kit that integrates cultural storytelling to teach high-level mechanical engineering concepts for less than the cost of a cup of coffee. In collaboration with Pueblo Science, we developed an add-on to their existing robotics kit to make it more engaging, accessible, and creativity-driven.
Our client wanted us to expand their existing robotics kits. Our constraints were absolutely no metal, to keep shipping costs low, to keep the total mass under 500 grams per kit, for there to be less than 2 hours of printing time for all the 3D printed parts in the kit, and for it to be compatible with the existing custom PCB. We benchmarked our assembly time to ensure grades 5 to 8 students can complete a functioning build in under 90 minutes. PUPPETRONICS isn't just a toy, it's a modular engineering system. We chose this design because it provides the mechanical depth missing from simple craft kits, allowing students to build real linkages that mirror the motions of their own local folklore. The kicker? Our final constraint is to keep the total cost per kit of our expansion under $2 Canadian. Let us walk you through how PUPPETRONICS is built. The foundation of the system is a 16-inch by 12-inch by 10-inch cardboard chassis, which houses the projection environment and features a window for the standard A4 screen. To ensure a sharp silhouette, a custom cardboard phone mount is used to align a smartphone flashlight, providing a high-intensity point source of light. The brain of the operation is the Pueblo Science PCB, which is securely elevated from the chassis using standoffs for electrical isolation. This board controls 2 micro servos that are held in place by a 3D printed servo mount, creating a stable, high-torque base for the puppet's movements. The animation is physically realized through a press-fit interface, where a Lego to servo 3D printed adapter connects the servo horns directly to Lego Technic beams. This mechanical linkage system translates the rotational force of the motors into the dynamic movement of the 2D cardstock puppets. On the software side, the system is driven by Blockly Pueblo via a dedicated Wi-Fi connection, allowing for wireless synchronization and precise control over motor speeds, ranging from 40 to 255 RPM and timing. By adjusting distance between the puppet and the light source, the operator can manipulate the shadow's magnification and clarity, resulting in a professional-grade digital storytelling platform built from accessible, engineered materials.
Now that we've covered the individual materials, let's see how they come together in the physical world. This is the PUPPETRONICS Shadow Theater prototype. As the Blockly Pueblo code runs wirelessly via Wi-Fi, you can see our servo to Lego adapters translating motor rotation into smooth storytelling motion. We managed to maintain high torque performance and precise tolerances while staying under our 500-gram weight limit and $2 budget.
The rationale behind each component reflects a series of intentional design decisions that guided the development of our final system. First, the box or chassis was made from cardboard with a front cutout for the stage. The main challenge was maintaining rigidity after cutting the opening, which we solved by using thicker cardboard. We chose cardboard because it's lightweight, low cost, and requires no metal, helping us stay under the 500-gram and $2 constraints. Second, the screen was made from A4 paper attached inside the box. The challenge was ensuring clear shadows, since wrinkles reduce visibility. Paper was chosen for its availability and low cost, supporting easy replication. Third, the phone mount was built from folded cardboard to hold a smartphone as a light source. This eliminated the need for extra lighting components, keeping the system simple and within budget. Finally, the puppet made from a lightweight 2D material. The main challenge was balancing flexibility and durability, which we addressed by selecting a slightly stiffer material, cardstock, to maintain its shape while allowing smooth movement. This keeps the design lightweight, low cost, and easy to customize.
And now we move on to 3D printed components. Finding off-the-shelf components that could bridge the gap between our custom PCB and Lego-style parts proved nearly impossible within our $2 budget and strict mechanical tolerances. To solve this, we engineered our own custom 3D printed suite. By designing our own servo mounts, PCB standoffs, and servo-to-Lego adapters, we achieved the exact dimensions required for high-performance movements without the high cost of specialized commercial hardware. This approach was also a massive win for logistics. By using lightweight, 100% non-metallic PLA, we kept the total mass well under our 500 grams limit, directly reducing international shipping costs while maintaining the overall durability and performance of the kit.
Finally, to reduce reliance on 3D printed parts and improve accessibility, we pivoted to using Lego-like technique components. They provided a great off-the-shelf solution for linkages, but they also threatened our $2 budget. To fix this, our team performed a full functional audit of the assembly. We identified which parts were absolutely essential and cut out the ones that weren't. By optimizing the design this way, we were able to keep the mechanism fully functional while bringing the total bill of materials back under the cost limit.
Ultimately, the Puppetronix project successfully met Pueblo Science's primary goal, creating a highly accessible, low-cost gateway to STEM. By delivering a verified prototype that hit a 1.9 Canadian dollar price point and weigh only 196 grams, we have proven that complex mechanical education doesn't require expensive commercial kits. The significance of this work lies in its scalability. We aren't just providing a toy, we are providing a platform that allows grade 5 to 8 students in low-resource communities to see themselves as engineers by using a culturally relevant storytelling medium like puppet theater. We remove the intimidation factor from robotics and coding. Ethically, our team prioritized safety and inclusivity. We proactively identify and mitigated physical hazards, ensuring that low cost never means low safety for the children using our kits. Furthermore, we ensure that the local folklore or the character represented in the Puppetronix are not misrepresented. For future work, there's always room to refine the assembly instruction and components tolerance. To ensure long-term durability, future adaptation will focus on optimizing material pairing to reduce wear between custom parts and Lego Technic components. Finally, we are hoping to be able to improve Puppetronix in such a way that will increase kids' engagement and love for STEM. Thank you.